Let's solve example 6. Here we have a cylindrical tank that's 4 meters tall, has a radius of 2 meters, and it's filled with gasoline up to a depth of 3 meters. We want to pump all of the gas out of the top of the tank, and we want to know how much work is required in order to do this. So let's start by drawing a picture here. We have a cylindrical tank. The radius is 2 meters, and the height of this tank is 4 meters. So this is 4. The radius is 2. And we're told that this is filled up to a height of 3 meters. So I'll draw in here, this is the amount of gas here in the tank. We're taking all of the gas and we're pumping it from where it is in the tank outside the tank. Now we could be kind of smart about this and imagine punching a hole in the bottom of the tank and then, well, all the gas would be pumped out without doing any work, but no, we want to actually pump the gas out from where it is out of the top of the tank. Now, the difficulty is the gas that's near the top here, where it's just 1 meter away from the top of the tank, that doesn't have to move very far. But if we think of the gas at the bottom of the tank, that has to move the entire distance of 4 meters. Now, that's not the way we normally think of pumping out a liquid. We'd think of doing it in a continuous, smooth fashion. But here, we want to think of taking discrete chunks of liquid and moving them out of the top of the tank. So we're going to imagine taking a slice of gasoline, which sounds ridiculous, but we're going to take a slice of gas here, and we're going to imagine moving that slice out of the top of the tank. So this is all a fixed distance from the top of the tank. Let's go ahead and label that distance as x. And this is the key. We're slicing thin enough so that this entire slice of gasoline is the same distance x from the top of the tank. If we can find out how much work is performed on just this slice, we can integrate to find the total amount of work. So we want an expression for the work performed on a slice of gasoline, which again just sounds strange. But work here, we have a small portion of work, dW. Work is force times distance. The distance is x, that's how far this slice of gasoline needs to move. And force, once again, is weight. So we have the weight only of the slice, not the weight of the entire amount of gas. So we have the weight of the slice, that's force, times x. Weight can be calculated by taking mass times 9.81. Now we need the mass of this thin slice of gasoline. How do we get the mass of that? Well, we were given in the problem the density of gas, and we want to think about units here. The density of gas is approximately 720 kilograms per meters cubed. Now, mass has units of kilograms, which is right here for the density expression. If we can find the volume of this representative slice, we can multiply by density. The meters cubes will cancel, and we'll have units of kilograms. So mass here can be written as volume times density. Again, let's think of the units. Volume, that's units of cubic meters. Density is kilograms per meters cubed, cubic meters. The cubic meters would cancel. We're left with units of kilograms, which is mass. That's exactly what we want. So we have volume times density. Density is 720. And the volume is just the volume of this representative slice. Well, this is a thin cylindrical disc, and the radius here is the same as the radius of the entire tank. It's 2. So we want the volume of this cylinder, which is pi times radius squared times height. There's the volume of that cylindrical thin disc. We still have the 720, 9.81 times x. Radius again is 2 meters. So we have pi times 2 squared. The height of this cylindrical disc is the small change in x, dx. That's the width of this thin slice of gasoline. So the height here is dx, And then we still have the times 720 times 9.81 times x. There's a lot going on here. This is quite the progression of steps. And let's think of units here to make sure that we're doing this correctly. So pi doesn't have any units. 2 was a distance, so this has units of meters. And then it's 2 squared, so meters squared. dx, that's meters. 720 is kilograms per meters cubed. 9.81 meters per second squared. X is a distance, that's units of meters. And a bunch of these units cancel out. Meters squared times meters cancels with meters cubed. We have kilograms times meters per second squared. That's newtons. Times meters. Newtons times meters is joules. That's our units for work. So the units work out correctly here. Double check that this progression here of steps makes sense, that it makes sense how to go from each of the different steps here to get to this final expression. Once we have this, we've really done all the work, pun intended, for the problem. To get the total amount of work, we integrate this expression. So total amount of work here is the integral. Let's put the dx at the end. And look at all the constants that we have. Pi, 2 squared, 720, 9.81. These are just constants. Really, the only variable is just x. So we have pi times 2 squared, which is 4, times 720, times 9.81, times x. What about the limits of integration? Well, the limits of integration are the values that we need for x in order to take all of the gasoline out of the tank. So x, we're measuring from the top of the tank. Well, we're not full of gas to begin with. This only has gas up to a height of 3 meters. So initially there's 1 meter of empty space here. So x is going to start at 1 and go all the way to 4. So the limits of integration are from 1 to 4. Again, all of this is just a constant. So we really have 4 pi times 720 times 9.81 times the integral of x dx from 1 to 4. Plugging this into a calculator, we have 665,691 joules of work being performed here. That's how much energy is expended in order to empty out this entire tank of gasoline. Let's work through example 7. A triangular tank with a height of 3 meters, width of 4 meters, and a length of 8 meters is full of water. We want to pump out all the water from the tank through a spout that's 1 meter above the top of the tank. We're told that the density of water is approximately 1,000 kilograms per meters cubed, and let's go ahead and work through this. So we'll start by drawing a picture. Here's our triangular tank. It is 3 meters tall, 4 meters wide at the top, and we're told that the length is 8 meters. We've got a spout here that's 1 meter above the top of the tank. So we'll draw in a little spout. This is 1 meter above the top of the tank. Now we're taking all of the water that's in the tank and we're pumping it out through the spout. Once again, we want to think of doing this in a piecewise or a discrete fashion. So rather than continuously pumping out all the water, we want to imagine taking some slice of water and moving that slice from where it is out of the top of the tank. And this sounds really strange, slices of water. Maybe we can think of this as ice or something, but the water that's near the top of the tank, this doesn't have to be pumped very far. That's only 1 meter that it needs to be pumped. But water near the bottom of the tank, well, this is 3 meters from the top and it has to go an additional 1 meter. The water near the bottom has to be pumped out 4 meters. So the difference here, the reason that we can't just use work equals force times distance is because the distance is changing. Distance here is just 1 meter. Distance down here is 4 meters. So we want to think of a representative slice of water that is the same distance from the top of the tank. So let's draw in a representative slice. And let's give the width of this slice a name. Let's say that it has a width of S. That will come in handy later. And we'll say that this is a distance X from the top of the tank. Now, we could measure x from the top of the spout. We could redefine what x means here, but for this problem, it will be easier if we choose x to be the distance from the top of the tank. It's solvable the other way, but it will be just a bit more convenient to define x as this distance here. So the width of this slice is some small change in x, dx, and now we want to think of how much work is performed on this one slice of water. So once again, we use dw for a small piece of work. Work here is force times distance. The distance is x plus 1. We have to move a distance of x to get to the top of the tank, and then the spout is 1 meter above the top, so an x plus a distance of 1. So distance here, x plus 1. Force is the weight of the slice. So we have the weight of the slice times the distance x plus 1. Weight is mass times gravity. And then mass, that's just the mass of this slice. And the way to get to mass is to find the volume of the slice and multiply by the density. We're told that the density is 1,000 kilograms per meters cubed. If we find the volume of the slice, that's measured in cubic meters, multiply volume by the density, and we'll have units of mass, which is exactly what we want. So we're going to write mass as volume times density times 9.81 times x plus 1. Let's double check the units here to make sure that they're working out. Volume is cubic meters. Density is kilograms per cubic meters. 9.81 meters per second squared. And then x plus 1 is a distance, that's meters. Cubic meters here would cancel. We have kilograms times meters per second squared. This is a measurement of newtons. Times meters, that's distance. Yes, indeed, we have joules. The units are working out, so we know we're on the right track. So we have volume times density, which is 1,000, times 9.81, times x plus 1. The volume is the volume of this representative slice of water. And we can think of this as a rectangular solid sitting here in the trough. It has a length of 8 meters. It has a width of s and a height of dx. So the volume is the product of those three. The volume is 8 times s times dx, length times width times height. Then we copy down 1,000, 9.81 times x plus 1. Now, we need to convert this expression s to be in terms of the variable that we're using, which is x. So since we're integrating with respect to x, and we have an x here, we need to convert s to be written in terms of x. We can do that using similar triangles. Consider taking just the front face of this triangular trough. Let's draw that. It has a width of 4, a height of 3. And let's imagine the little slice of water here in this cross section. It's right about there. This width is s. And this blue triangle is the same shape as the big triangle, just a different size. So since we have a similar shaped triangle to the overall one, we can use the concept of similar triangles. This distance is x, and since the overall distance here is 3, the height of this small blue triangle is 3 minus x. So I can write a ratio of corresponding sides. I have the width of the small triangle divided by its height. That equals the width of the overall triangle divided by its height. We can use this now to solve for s in terms of x. S equals 4/3 times 3 minus x. Now that we've written s in terms of x, we can use it in this expression and find the total amount of work performed. So the total work is the integral of all these representative slices of work. We integrate 8 times s. S is now 4/3 times 3 minus x. We'll put the dx at the end. We have 1,000 times 9.81 times x plus 1. And what are the limits of integration here? Well, the limits of integration need to be the values for x that get all of the slices of water. So x starts at a distance of 0. This is how we define x, the distance from the top of the tank. The tank is full, so x starts at 0 and goes all the way down to a distance of 3. That's the total height of the tank. So the limits of integration are from 0 to 3. Now this integral looks quite messy. We have a lot going on here. But notice that most of these things are just constants. Really, we have a 3 minus x times an x plus 1. If we expand that out, that's just a polynomial. This is actually a simple integral. We just have a lot of constants that make it look unpleasant. If we evaluate this integral, we'll get a value of 941,760 joules. That's how much work is done in order to empty all of this tank. Take a look at example 8. In this problem, we're going to find how much work was performed in order to build the Great Pyramid of King Khufu. Now, in the previous section on volumes, we found how much volume this pyramid consisted of. But in this section, we're going to figure out how much work was performed in order to build it. So once again, we'll start by drawing a picture. We have a square base, side length 756 feet, and then its height is 481 feet. Now we want to figure out how much work was performed in order to move all the blocks of limestone from where they were at ground level to where they are in the pyramid. So if we think about this, near the base, those blocks don't need to be moved very far. There's not too much work involved for those. But as we get higher, the blocks near the top of the pyramid had to be moved further, so there was more work involved per block for the blocks near the top of the pyramid. So we want to slice this up so that the work performed on just a slice of the pyramid was a constant amount for a constant distance from the base. So we'll take a horizontal slice of the pyramid here and figure out how much work was performed on this slice. Let's say that this slice is some distance h from the ground level. And then this slice has side lengths, we'll say s by s. So once again, we'll set up an expression for the work performed on a slice. This is some small amount of work, dw. Work equals force times distance. The force is the weight of the slice. Distance is how far it's been moved, which is a height of h. Let's think of the units here. Weight is measured in pounds, and height is going to be measured in feet. Final answer for work here will be measured in foot-pounds. So if we want to think of how to get the weight for a slice, well, we're going to take the volume of a slice times its weight density. So we're told here the weight density of the limestone is about 150 pounds per cubic foot. So we'll write down density is 150 pounds per cubic foot. And if we imagine multiplying this density by a volume that's measured in cubic feet, then we would have units of pounds left over. So in our expression here for the work performed on a slice, the weight can be written as volume times weight density. So we have volume times density times h. Volume is the volume of this thin rectangular solid slice. So we have measurements of s by a little bit of height. The height here, as usual, is small change in h, dh. So we have s times dh times the density, which is 150, times h. So s squared dh times 150 times h. Once again, we have an issue here. We have two different variables. We have s and h, and we might suspect, given the nature of the problem, that we'll use similar triangles to write s in terms of h. So let's imagine taking a cross section measured vertically. That looks something like this. Here's the overall pyramid. This is 756. The height here is 481. And our representative slice is sitting right here somewhere in the pyramid. This is a distance of s. The height above the ground is h. So this distance, the height of our small triangle here, that will be 481 minus h. So now we have two similar triangles. Here's the small red one, same shape as the large black one, just a different size. So we take the width of the small triangle divided by its height. That will equal the width of the overall triangle divided by its height. And we have a relationship that allows us to write s in terms of h. So s divided by 481 minus h equals 756 divided by 481. So we have s equals 756 divided by 481 times 481 minus h. Now we've written s in terms of the variable h. Now we can write the total amount of work performed. The total amount of work will be the integral of all these representative slices. S is now written as 756 divided by 481 times 481 minus h. There's our value for s. We're squaring all of that. So there's s squared. And now we multiply by 150 times h, and the dh we'll place at the end. Now, in order to add up all of the amount of work, we need to integrate in terms of h, and h starts at 0, the height of 0, and goes all the way up to the very top of the pyramid, which is 481. So the limits of integration here are from 0 to 481. This integral describes how much work was performed to move all of the limestone from ground level to its position in the pyramid. Now, this looks rather messy, but we have a lot of constants here that we could take out. If we expand this all out, really we have a polynomial. So integrating this wouldn't be terribly difficult, but if we plug it into a calculator, the answer that we get is a very large number. It's approximately 1.65 trillion joules. That's an enormous amount of energy required to build this pyramid.